I will revisit this example, the global register allocation example. So I will revisit this example, and I will also give an example for code generation for nested loops. Okay. So why revisiting this example? Because I noticed that many students are still having difficulties with the concept of a live range, and why when we spill, we avoid interferences. So first of all, the live range of A, it starts with a definition and it ends with this use, and there is another parallel live range here in which A is being used. So what this means is that the live range of A is like this and this. So A is live throughout this entire basic block. Now what does this mean? It means that anything that we do here will not prevent B and D from interfering with A. They will still interfere with A because A is live throughout the entire block. But we can do some things that will eliminate the interference between B and D. So the first thing that we did, we tried to spill B. So we did define B and store B. Spill is store. By the way, sometimes I use spill and store interchangeably because spilling is basically storing in memory. So store B, and then we load B again, and then we use B. Now, what we should keep in mind is that a store, is it a use or a definition of a register? Does the store use or define a register?
It would define a register, wouldn't it?
No, it's a use.
It's a use. It uses a register and it puts it in memory. So a use is a read. Use is the same as read, and it's the same as input, operand, or source operand. So these are the same thing. Using, what you use is the input, what you consume, okay? And the definition is what you produce. So define is write, produce, output operand, destination operand, okay, you name it. So given this, a store uses a register. So a store counts as a use of a register, and a load defines a register. So it counts as a definition. So in this case, when we store this, this is a use, and this is a define. So basically, we are introducing now a small live range with this definition and this use when we spill B. And here, we are introducing a new live range by the load, because the load is a definition. Remember, load defines a register. So it's a definition. It produces a value into the register. It puts a value. It writes a value into a register. So it's about a register. It's about the register, not about memory. Does the load write or read? It writes into the register. It reads from memory, but it writes into the register. So it's all about registers. From register point of view, a load is a write, and a store is a read. So this is a define. This load is a define, and this is the use. So basically, we have split this live range of B. Instead of keeping B alive, we stored it here. So this is one small live range, and this is another small live range that starts with the definition, because the definition within this block is going to start a new live range. Because this use here is going to use this definition. Now, even if we do this, we did not eliminate the interference. Because if we call this new live range D1 and this live range D2, And this is the live range of D. Now D interferes with, it no longer interferes with D1, but it interferes with D2. But this didn't help because we're still having an interference between D and one of the B's. Okay? So that's why spilling B here did not help. While when we spill D, let's do it in blue, spilling D means insert a store here. Storing D, now we store it in memory. Now we no longer have this live range for D. Because now we are not keeping D in a register, we just stored it in memory. We spilled it. This is no longer the live range for D. Now this is the use of D. Okay. Now before the use of D, we're going to insert what?
A load.
A load or a new define. Okay. Now we have two. Again, we have split the live range of D into two small live ranges. This is defining D and using D. This is a small live range for D. And this is another small live range for D, the load and the use. So the load and the use, the load which is a define and the use, and the define D and the store D. So this is a define, this is a use of D. So now these blue live ranges for D, they no longer interfere with, okay, I should have said B, not D. Okay. B1, B2. Okay, so now these small live ranges now, they no longer interfere. And now we eliminated the interference between B and D by spilling D. Okay, so I hope that this clarifies how spilling eliminates interferences between registers. Now spilling by adding a store after every define and a load before every use, this is extreme splitting of the live range. Because by doing this, we are splitting the live range into tiny little live ranges, and each live range has only two instructions in it. You know, for example, here, the define and the store. So by, let me write this down. Okay, is spilling by adding, or let's say inserting a store after every def and a load before every use is an extreme way of splitting the live ranges. Splitting live ranges. It splits possibly long live range into a number of tiny live ranges. Into a number of tiny live ranges, with each live range consisting of only two instructions. You know, the load and the use, and here the define and the store. Into a number of tiny live ranges, with each live range consisting of two instructions. def and store, or load and use. So sometimes this extreme spilling by inserting a load before every use and a store after every definition may not be necessary. It may be efficient to do some more moderate kind of splitting. How? So let's look at this example now. No, I guess now you are done with this example. I think you're probably sick of this by now. You have seen it a lot. So we are done with this. So now we are looking at a different example, an abstract example. What if you have something like this? Define A, use A, some other instruction X, some instruction Y, use A, instruction Z, use A, define B, some instruction. Okay, so we can put instruction A, instruction B, and then use use B and use A. Now in this case, if the register allocator chooses to spill A, if it chooses to spill A, it's going to insert a store here. Then it's going to insert what? A load before every use. Load. So it's going to insert loads before all the uses of A. This is extreme. Sometimes in this case, in this particular case, for example, in order to eliminate the interference between A and B, so this is B, this is the live range of B, so we can eliminate the interference between A and B here by keeping A in a register throughout this live range and then loading A again here. So by splitting, but not extreme, this is not extreme splitting. This is moderate splitting, or it's a smarter way of eliminating the interference between A and B. What we do here is we keep A in a register. We keep A in this register, and before this use here, we just load A. So by adding this load A, we are splitting the live range of A into this live range. So this is no longer a tiny live range. So this is a live range that has 3 uses. So it's quite significant. So this is a live range. It's shorter than the original live range, because the original live range is all of these instructions. So this is the original live range. So this is shorter than the original live range, but it's not as tiny as those the tiny live ranges that you get when you add a store after every definition and a load before every use. So when the register allocator considers splitting, it may generate much more efficient code, or in other words, it will generate fewer loads and stores. So it's all about how many loads and stores the register allocator is going to generate. Ideally, we would like to generate none. We would like to avoid generating loads and stores. If we can fit all live ranges into physical registers, we will not have to insert any loads or stores. But if we have to, we would like to minimize them. And that's why register allocation is a hard problem in compilers. And that's why no existing compiler, to my knowledge, has a perfect solution to this problem. So any compiler that you use, it may, in some test cases, or in some cases, it may generate more spills, more loads and stores than necessary. Yeah.
With the current technology, the CPUs and stuff, the loads and stores, wouldn't the cache help mitigate the penalty for doing that?
Yes, definitely. Of course, if they hit in the cache, the penalty will be less. In fact, you would expect them to hit in the cache most of the time. Otherwise, we are dead. It's spill code is likely to hit in the cache.
Yeah.
But even if it hits in the cache, it is still a memory operation because it uses memory bandwidth and it takes 2 or 3 cycles as opposed to 1 cycle for a register move or just performing an operation on an operand that is already in a register. So if you are doing this add R1 and R2, if you are performing this operation and R1 is already in a register, it's definitely much faster than having to load R1, even if R1 is in the cache. So even if it's in the cache, you are spending 2 to 3 cycles to load it. You are using resources. You are using an instruction. You are adding the instruction count. So the instruction is taking an issue slot in the machine. It's also taking place in the iCache. It's taking all kinds of resources that an instruction takes. So you are adding an instruction, and an instruction can never get executed for free. So it will use some machine resources, issue slots, execution units, iCache. Okay. Of course, if the spills miss in the cache, that would be a huge penalty. But usually they don't because it's because of the locality of reference. So if you are, for example, this is if you store something, if you store this A here and load it within a few instructions, then it will be in the cache, right? So if you access it, usually the accesses are within a small number of instructions. So if you re-access something within a few instructions, this is temporal locality. You are accessing this frequently. You are accessing the same memory location. So spill code is likely to hit in the cache. Will hit most of the time.